Welcome to the Sundance Media Group AVOC. My name is Douglas Spotted Eagle, and I'm going to take you through our night CSI program and how we generally work. Now, there's a few tools that we use that you're not seeing right now. The first thing we use is the Fox Fury T56 scene light. These lights are colored gray, and the light that they emit is daylight balanced at 56K, so they're perfect for crime scene capture late at night or in nighttime environments. They also can act as augmenting lights when you're in areas where you've got murk vapor or halogen lighting or even just headlighting that is polluting or contaminating the color of your particular scene. The next thing that we're going to be using is this is a DT Research 301 tablet with the RTK built into it. Now, this is a very unusual tablet. It's not only a ruggedized tablet made specifically for construction, law enforcement, and other rugged types of environments, but on the back of it, it's got a LiDAR system that allows us to actually do live scene scans. So if we need to scan a body, if we need to scan an officer in the event of an OIS, or if we're in the construction world, we can use this as a great tool to scan pipes and digs and trenches and so forth and mark exactly where things are located in the ground. So we're going to be using this coupled with evidence recorder in the system here. And then last, we're going to be using the Autel Evo2. This happens to be the Pro model, or what they call the 6K model. So this one's got a 1-inch 6K imager built into it, and it operates in tandem with what is called the live deck. So these two work together so that during the mission and while the mission's flown, we can see exactly what the camera is seeing on the monitors inside of the AVOC here and see what's happening behind us. So the first thing that's going to happen is we're going to arrive on scene. We're going to discover our subject, or in this case, a mannequin in our mock homicide. And so with that and no further commentary, let's get right to it. Once on scene, the first thing that is going to be done is to identify the target of the shoot or the target of the evidence capture. We'll begin to bring out lighting. Now, of course, this area needs to be kept pristine. And so as the technicians are carrying out the lighting to the scene, they're going to set them up at a predetermined distance, usually somewhere in the range of 25 to 30 feet away. And they'll pull out a laser measuring device to measure the distance from the first light to the object of the scene, or the subject of the scene. In this particular case, you can see that laser flashing around and identifying distance. So this laser is used to measure distance from the lighting source to the subject. And this measurement will be used throughout the entire scene on all of the different lighting setups. In this particular case, we're going to set up 4 lights. This can be achieved with only 3 lights, but it is best achieved with 4 lights so that we can get even measurement or even light fall off on all segments of the subject. One thing to note as this second light is turned on is that the light is not pointed directly at the subject, but rather pointed slightly down to the ground so that it is more the fall-off lighting or the peripheral lighting that strikes the body. This helps to reduce shadows, and so if we look at this from an overhead view, when we do look at this from an overhead view, note that the harsh pool of light is directly at the base of the light stand itself as opposed to being on our subject. Once the 4 lights have been placed, there will be some adjustment. It's inevitable that the very first setup will not be perfect. And so what will happen is, again, we'll be using the laser device to measure distance to make sure that we keep it equidistant, but the whole point is to reduce as many shadows around the subject as we possibly can. On occasion, it's necessary to put in a fill light. So in this particular case, we're using a Fox Fury Nomad light, a Now 56 light that is going to light up the area that's in between the legs of the subject there. Now again, notice that the light is not being shined directly on the subject, but rather allowing fall off to fill in those shadow patterns. After lights have been set, ground control points, otherwise known as GCP, are placed around the scene. These will be used to lock the aircraft to the ground in regards to the GPS positioning. This is required in order to ensure sub-centimeter or centimeter accuracy on any scene. Once the GCPs are set, a sky ruler is placed as a scale constraint. This ensures that we have a fixed physical device from which to check our measurements. Finally, a launch pad and a launch area are set up. This is always done last to prevent people from stepping on top of the drone or accidentally getting into the launch area and damaging equipment. Next, we will be using a GPS recording device. In this case, this is a DT Research 301 system. This has got a built-in LiDAR for scanning on scene, which works great in the daylight hours. It does not work so well in nightlight. With this, we're going to use Evidence Recorder, and this allows us to record and capture specific GPS points. Notice that our accuracy is very, very tight in this particular scenario. Once the GPS point is recorded, it is stored, and eventually will be exported as a text file when it comes time to build this scene in Pix4D. Last but not least, we're going to mount our Fox Fury D3060 lights. These are the only lights that are currently authorized by Autel for this kind of use on the Autel Evo2 drone, which is being used in this particular scene capture. At the same time as the lights are mounted, a pre-flight safety check will be performed on the aircraft to ensure that all props are solidly attached, that the batteries are fixed, that the gimbal is working properly, and all components of the aircraft are working as they should. Just imagine how terrible it would be if the scene were corrupted by an aircraft brought in by a law enforcement agency. Next, the pilot will plan the mission. In this case, we see the pilot creating a cross-grid platform that is going to allow flight both north-south and east-west. So the aircraft will fly back against itself, capturing images in both directions. This ensures the best kind of capture, or the best capture method, for capturing photographs from all angles. We'll also incorporate an orbit to capture oblique images. Prior to flying the mission, the pilot will place the aircraft over top of the scene and manually set exposure for the best images possible. This is critical during night CSI captures. Simply putting up the aircraft in an auto mode rarely works. So by checking exposure prior to the execution of the mission, the pilot ensures that this is a one-and-done flight. After the mission has been captured and the aircraft has been returned to the ground, we're now going to make multiple copies of all images onto a computer hard drive system. We're going to open up Pix4D, and in Pix4D we're going to determine where those pictures will live and which images we wish to import. In this particular scenario, we're importing the nadir images first. We're checking to make sure that the Pix4D application is set up for a linear rolling shutter, and then next we convert meters to feet. Once this is done, Pix4D will import all of the images. We'll then determine what kind of map we wish to create, and for this particular demonstration, we're going to select a rapid map as opposed to a full resolution map. Once those images begin to import, we can see there inside of Pix4D where the drone was flown. Currently, we're setting a processing area, and this allows Pix4D to ignore any images that are on the outside of our particular flight path or undesirable images. We're also just double checking to make sure our images are exactly as we'd like to see them be. So again, in this case, we're setting it up for a low resolution, high speed render. We can always reprocess these at full resolution later on. After we have verified all of our settings, we're next going to import our ground control points. So we're going to go into the GCP MTP Manager. We're going to browse for the text file that was exported
from our DT Research RTK capture system. Now in this particular case, we've placed 4 GCPs. We can see the projection of where those GCPs will be, and we're going to start processing our initial point cloud. And you'll notice as the system begins to compute its key points here and begins to match and calibrate all of the images. This issues a quality report here that tells us exactly what has just transpired in our image. It shows our flight path. It shows the images and projections. So now we're seeing our initial point cloud put together, and we can see that our projected points are a little bit above the ground. So that means we've got some calculation or projection error. So now what we're going to do is zoom in on each one of our ground control points, and we're going to place markers inside of them to help the computer understand where the actual point is. So this is where we're tying our satellites from space down to the ground at ground level. So this is what the RTK point system does for us. It allows us to have absolute versus relative accuracy. Now, again, this kind of an RTK system is not entirely necessary for many types of uses, but if your measurements are critical and must be absolute, you're going to need some kind of an RTK system. Now notice here that as we place these marks in here, the marks began to self-center themselves. So in other words, as we click here on this first number 1 and go click on the second number 1 indicator that's here, Pix4D automatically makes some very intelligent guesses as to where the center of each of these next pieces in the ground control points are going to be. And this is significantly helpful as it saves a tremendous amount of time. We'll apply the markers and go to our next RTK point. We'll click there and zoom out just a little bit so we can find that particular RTK point. Now, one thing of note is we're using 2 different ground control point systems here. We're using a system from Hoodman that is their standard ground control point system. That's the orange and black. They also have a ground control point system that's made specifically for LiDAR. And these are the black and white reflective systems that you see. Both work identically well. We've used both, and in some cases prefer the black and white, particularly when we're dealing with nighttime structures. They work well, both systems work equally well, so it's really a matter of which preference. And you can find these ground control points at hoodman.com. We're just about through placing all of the marker points. Again, we're centering in on that tiny grommet, the same place where we centered our RTK system when we were first capturing those points. So this is giving us an idea, or showing us the difference in projected versus actual measurements. We're going to now re-optimize. That generally happens very, very quickly. Here's our images again, and note that everything is now tied exactly to where it should be, so we're ready to move on to our next step. We're going to turn off point 1 and turn on process number 2. And you'll notice that again, it's initializing all 133 cameras and grouping them and calculating points. So we're just already starting with a mere 10,000 points. This will grow significantly, as you can see in the image here. This is going to generate our point cloud, and this is what is generally used for most measurement systems. The easiest way to describe a point cloud is to think of making a papier-mâché model, where first we start out with somewhat of a chicken wire frame or a wire mesh that sits underneath. And that's similar to our point cloud, our initial point cloud. Then on top of that, we lay newspaper that's been covered in glue, and that begins to gently cover over our various points. And this is what you'd refer to as the actual point cloud. Last but not least, we'll lay over top of that other material and start to fill out the framework, and that would become what we would view as our texture. So now we're just using that point cloud. We're going through and we're checking our measurements here. We want to be sure that what we see there is a 60-inch measurement, because that is the size of our ruler. Now we can use this information here where we've measured the ruler as what is referred to as a scale constraint. Once we set this, we can tell Pix4D that this was what 60 inches or 5 feet looks like, and we can verify all of our other measurements from that point. But because Pix4D is already very accurate, you can see here, for example, we're looking at approximately 1.3 feet away from the hand of our victim, and we can see all the various points of our point cloud laid out here. Now notice that the edges are square. You might remember when we first ran this that we had a processing area that we adapted to our flight map. Now we're refining that area. So now we're working with a much tighter area. When we refine these processing areas, we're not cutting out any information, we're merely hiding information that we don't want to see. So for purposes of forensic access, this can always be re-expanded to see everything, every image shot. So here we have our point cloud mesh. From here we can run our orthomosaic and other indexes. So it's a fairly fast process all the way through. Again, remembering that we're operating at a 1/8 scale. So in a full scale environment, a scene like this is going to take approximately 2 hours to render, depending on the speed of the computer and the amount of available RAM. Once these processes are complete, there are several other things that we might do inside this image, such as opening up the Mosaic Editor and cleaning up some of the various locations in the scene. We might go into the point cloud editor and remove, for example, the lights or the bushes or other elements that are in the scene that we might not wish to see for purposes of display. However, those items are never deleted, they're merely hidden. So this is one of the primary benefits of using Pix4D in these kinds of scenes, is we can not only create an orthomosaic map that people can look at, but we can also create a 3D model that can even be walked through using VR goggles or any number of other things. So this is just the beginning of some of what we can do with the Pix4D application and using an Autel Evo2 aircraft capturing these kinds of scenes.
So as you can see here, we've rendered this out in a low resolution format, but it still looks pretty doggone good. So if you'd like to play with this project, just simply click on the links that are down here below and it'll take you right to this project, and you can play with it as much as you would like to and get an idea of how Pix4D Mapper will work in your own workflow. You can even download these images yourself and play with them as much as you'd like to. If you have any questions, feel free to email us. Just simply contact us at requests@sundancemediagroup.com. We hope that you're going to have a great time here at ComUAV. It's always been a great show for us, and we're certainly grateful for the opportunity we've had to spend a little bit of time with you.